Autocorrelation. What do you mean by autocorrelation? When the successive value of the random variable, that is u, are interrelated with, then the autocorrelation problem arise. That is, the correlation between the error term uj and ui, it's not equal to 0. That means I not equal to j, then autocorrelation is a special case of correlation, and it refers to the relationship not between two or more variable but between the successive value of some variable. For example, the subscript of u its change, and we use t minus 1, t minus 2, t minus 3 up to t minus s. Thus, the relation between ut comma ut minus 1, ut minus 1 comma ut minus 2, ut minus 2 comma ut minus 3, and so on represent the autocorrelation. So the autocorrelation can be represented as correlation ut minus 1, it's not equal to 0. That means there is a relation between the error term. Suppose consider y is equal to x beta plus u means error term. It's in the next line taking expected value of the error term, it's equal to 0 for all t, and expected value of the ut prime, it's equal to sigma u square omega. This is a non-spherical model, that is why consider omega, but in case of spherical model uh, we consider sigma u square I. Because the reason of non-spherical, there is a problem of autocorrelation, that is we consider omega. Let us consider the sth order correlation covariance, that is covariance is ut minus s is equal to expected value of ut minus s minus expected value of ut into expected value of ut minus s, that is equal to expected value of ut minus s, it's equal to gamma subscript s, where s is equal to plus minus 1 plus minus 2 plus minus 3. So variance of ut is equal to expected value of ut square, and it is equal to gamma 0. Here s is equal to 0. Thus, sth order correlation coefficient will be rho s. Rho superscript s is equal to covariance of ut comma ut minus s. There is a relation between ut minus s and standard deviation, divided by standard deviation of ut and standard deviation of ut minus s. So covariance ut comma ut minus s is equal to gamma s. From this line I can show that from here, and divided by standard deviation of ut into a standard deviation of ut minus s, this is shown in this line. So standard deviation or variance of ut, it's equal to gamma 0. Now come to the next page, that is, now we can write the dispersion matrix of error term as expected value of u prime, it's equal to, it's a matrix, the variance term are all gamma 0 and the covariance terms are different, so we can represent it as gamma 0 gamma 1 gamma n minus 1 gamma 1 gamma 0 up to gamma n minus 2, and in the last row gamma n minus 1 gamma n minus 2 and up to gamma 0. Here all the variance term are equal, because the homoscedasticity assumption follow. If we take common gamma 0, then the whole matrix is 1 row 1 p superscript n minus 1, and the next row 1 1 row n minus 2, and in the last row n minus 1 row superscript n minus 1 and up to 1. To determine the value of dispersion matrix of gamma, let us consider first order autocorrelation, that is ut equal to rho ut minus 1 plus epsilon t when rho mod of rho is less than 1, and it is known, it is called the coefficient of autocorrelation. So ultimately rho term, rho is correlation coefficient, so it is mod less than 1 its value. And if the value rho is not known, we can determine it easily. When epsilon t its error term, epsilon t means we can show that this epsilon t is error term, its error term, and it is spherical in nature, then expected value of epsilon t is equal to 0 or null. And in the spherical model, I already mentioned in the previous lecture that the expected value of error terms, it's equal to 0, and expected value of epsilon t and epsilon t prime, it's sigma sigma epsilon square into I, because I it's considered in the spherical model. So in the next line, ut it's equal to rho first bracket rho ut minus 2 plus epsilon t minus 1 plus first bracket third bracket close or first bracket close plus epsilon t. So if we multiply, we get rho square into ut minus 2 plus rho epsilon t minus 1 plus epsilon t. And similarly we can put the value ut minus 2. So rho square ut minus 2 means rho ut minus 3 plus epsilon t minus 2 bracket close plus rho epsilon t minus 1 plus epsilon t. So in the next page I can show that expected value of just arranging this equation in such a way that is epsilon t plus rho epsilon t minus 1 plus rho square epsilon t minus 2 plus rho q epsilon u t minus 3. As we produce in this way the term u values first, epsilon value first, and ut error term it's equal to epsilon t plus rho epsilon t minus 1 plus rho square epsilon t minus 2 plus up to. So ut is equal to sum of s equal to 0 to epsilon 0 to infinity rho power s epsilon subscript t minus s from this line. And expected value of ut, taking expectation both side of the equation from this equation, and expected value of ut is equal to expected value of epsilon t plus rho epsilon t minus 1 plus rho square epsilon t minus 2 plus infinity. So it's equal to expected value of epsilon t plus rho expected value of epsilon t minus 1 plus rho square expected value of epsilon t minus 2 plus. So it is 0 because we know that the expected value of epsilon t, expected value of expected value epsilon t minus 1, expected value epsilon t minus 2, its all values are equal to 0. And now come to the parts of variance covariance matrix, but this part will come to the next part of autocorrelation. So up to that I only considered the expected value of the error term, it's 0, that is proved here. So thank you.